of the given members using international codes. In the last lecture we saw an example problem, the member subjected to axial compressive force. We examined the adequacy of the design by using equations given in ABS 2008. In this lecture we will take up another example 2, where I will show you how a design adequacy can be checked for a given member with the data as given in the blackboard here. The diameter of the member is 1000 millimeters, thickness is 15 millimeter, Young's modulus of the material is given, yield stress value is given, length of the member and effective length factors are given, and axial force applied on the member is 1 meganewton, whereas the member is also subjected to bending moment of 1000 kilonewton meter. Now there is a combined action of axial force and bending, and the platform is under normal operating conditions. Let us see how I will examine the adequacy of this member using international codal provisions given in the codes. So let us as usual start with step number 1. Let us say the cross sectional area, so the thickness is 15 millimeter, let us say compute axial compressive stress, which is P by A, which I call as sigma E. Let us compute the moment of inertia, mm to the power 4. Let us work out the radius of gyration. Now I want about the minimum axis, but being a circular member, about x and y will be same, which is nothing but root of I by A. Which works out to be 348.27 millimeters. Let us work out the polar moment of inertia I naught, which is Saint-Venant's constant capital K, so for a tubular section K is given by Euler's buckling stress sigma E eta So, 0.8 is the factor of the effective length and length is overall length is 15 meters. So, pi square EI by KL by RY by square. So, I get this value as 1664.55 Newton per mm square. Warping constant is 0 because the section is symmetric and circular, and DCS, the distance between the centroid and the shear center, is again 0 for the section being symmetric and circular. So, in step number 1 we compute all the basic parameters and derive certain equations and formulas. Depending upon the values I substitute them and get the basic values which are generally required for the design check. Let us do step number 2 now to establish the compact limit of the section. I want to check whether the section is compact or not. Ladies and gentlemen, you will agree now that if I establish the section is compact, then I can always say the buckling failure will not prelude the axial compression acting on the member. So, I have to establish whether the given section remains compact for my dimensions. So, d by t, if it is less than E by 9 sigma naught, then I can say the section is remaining compact. In my case it is 1000 by 15 and the value is 2 10 power 5 by 9 of 240. So, this is 66.67 and this is 92.59 is less, section is compact. Here also there is a major check. Whenever you get a non-compact section, it is advisable to convert the given section to a compact section either by decreasing the diameter or by increasing the thickness, because having compact sections in the design is always advantageous. So, step number 3, to find the adjustment factor and maximum utilization factor. for static loading, the utilization factor is 0.6 of psi and psi is 0.87 if sigma EA is less than or equal to P r sigma naught. Sigma EA we have to compute. So, let us compute the elastic buckling stress sigma EA from the quadratic equation So, in my case, since dCs is 0, this term goes away. I know I naught and I know A from the first step. I know sigma E eta, just now I computed. I have to compute sigma E t, which is the torsional elastic buckling stress. If I know this, by solving this quadratic, the only variable sigma E A, which is an unknown, can be computed. So, sigma E t E k by 2.6 I naught So, gamma in my case, which is the warping constant, remains 0 because section is cylindrical and symmetric. So, this term goes away, I have only one term here. Let me substitute this 2 10 power 5 k we already computed in the first step, Sine-Venant's constant, So, I know all the values now. I know all the values because I have sigma E t here, sigma E eta I already have computed, sigma E A is unknown in my equation, I naught and A I have already known from the first step. Let me substitute, solve the quadratic and get sigma E A. Solving the lowest value (1690.57). Step number 5. to compute sigma Ca. The critical buckling stress sigma Ca is given by two equations. Directly sigma Ea, if sigma Ea is less than P or sigma F, otherwise it is given by sigma F of PR if sigma Ea is greater than. Now sigma F can be as same as sigma naught, which is 240 in my problem. So naturally sigma Ea is greater than 0.6 of sigma naught. Sigma naught is 240, hence sigma Ca is given by the second equation, sigma F of 1 minus Pr of 1 minus Pr of sigma F by sigma Ea, substituting 240 of 1 minus 0.6 of 1 minus 0.6 of 240 by 1690.57, which I get as 231.82. Step number 6, to check the adequacy for combined action of compression and bending. This is where the problem is different from the previous example. If sigma A by sigma Ca, if it is less than 0.15, then the equation is different for checking this adequacy. If it is more than 0.15, the equation is different. This is given in class 2 5.3 of ABS 2008. Let us check whether this is satisfied or not. So 21.54, that is what I computed from the first step. Sigma Ca I just computed 231.84. This value comes to 0.093, which is less than 0.15, hence the governing equation for checking the adequacy under the combined action of compression and bending is given by this should be less than or equal to 1. This is what famously called as unity check, because all equations you will see they are all compared with the number unity. In the present case, the section is compact. We have already established it in the first step. N1 is 0.6 psi and psi is 1 minus 0.13 of this equation, because this is true because for sigma Ea greater than PR sigma naught is the case what we have now. So, let us substitute here 1 minus 0.13 of root of 0.6 of 240 0.962, and therefore N1 is 0.6 of 0.962, which is 0.5772. So, I get two factors now. N1 is for axial compression, N2 is for bending, because it is a combined action of compression and bending. I have found out for axial compression now, let me do it for the bending also. N2 is for the combined action, this is taken as 1 in the specific case, this is as per class 1.9 of ABS 2008. Sigma By in this equation is simply m by z. Let us compute z as I by y max. In my case it is going to be so sigma By is m by z, m is Newton meter by 1.126 10 power 7. Let us rewrite it here again. Sigma By m by z 1 10 power 9 by 10 power 7, which gives me 88.81 Newton per mm square. Sigma Bz in my problem remains same as sigma By, which is 88.81 Newton per mm square for my problem. I must compute critical bending stress CBY is given by class 2.3 . For the compact section, that is d by t less than or equal to E by 4.5 sigma naught. Let us check this. 1000 by 15, which will be obviously less than 2 10 power 5 by 4.5 of 240, because this value is 66.67, this value is 185.185. So, this condition is satisfied. Then sigma CB is given by couple of equations, which is given by SMP by SME into sigma naught if sigma naught d by et is less than 0.02. Now, let us check this ratio. Sigma naught d by et in my problem 240,000 to 10 power 5 15, which is 0.08, which is higher than 0.02, then sigma CB is given by 1.038 minus So, let us say SMP and SME are the plastic section modulus and elastic section modulus of the given section. If I know the ratio of these two, I substitute here, get my critical bending strength which is allowed in the section. Let me get this SMP and SME. Given by 1 by 6 of d cube minus d minus 2t the whole cube. Substitute SME simply I by y y is nothing but d by 2, I get 500. So I have the ratios of these two plastic section moduluses, that is plastic section modulus and elastic section modulus, substitute in sigma Cb. So sigma Cby is 1.038 minus 1.9240 into 1000 by 2 10 power 5 into 15 multiplied by 1.455 by 1.126. Into 240. Okay, there is a multiplier here, I missed out in the last one. So this is into sigma naught. So that sigma naught in my problem is 240. So substitute that, get the value as 274.77. This is my sigma Cby. I keep the same as sigma Cbz for my problem. So last step, checking the adequacy, come back to the same equation, sigma A by Youngman sigma Ca plus 1 by N2 of sigma By by Cby, permissible value Bz by Cz, the permissible value raised to the power half. Let us check this. This should be less than or equal to 1, that is the unity check. So let us substitute them. So 21.54 by N1 we already computed 0.5772 of sigma Ca. Sigma Ca we already computed in the last step, which is 231.84 plus N2 has taken as 1, (88.81) sigma By already we computed that. Substitute these equations, you get this as 0.618, which is less than 1. So the section is safe, or I can say the section is adequate. So one can check the design for a combined action of compressive force and bending or pure axial compression with the help of these two examples, which has been demonstrated, and the equations have been derived and used as from the international codes. So ladies and gentlemen, these two lectures, the last one and the current one, will help you to look at the uncertainties in the checking process or adequacy process of the given design, and we must certainly agree and understand that in offshore structures the design is not done, only the adequacy of the existing assumed dimension of the members are checked. So once it is safe, we consider that whether the precluding buckling will not occur, the section will be safe in axial combined action of axial compression force and bending, etc. So we check only for the adequacy, and that is where we overrule certain uncertainties available inherently in the design process. So thank you very much. In the next lecture we talk about some more advancements in materials and structures. Thank you.